The global climate system is undergoing continuous shifts, but every once in a while a major atmospheric pattern emerges that dramatically reshapes weather behavior across the planet. And one of the most powerful of these patterns is El Niño, a natural climate phenomenon that originates in the Pacific Ocean, but influences weather systems on a global scale, including rainfall patterns, temperature changes, and most importantly, the intensity and frequency of hurricanes. And in recent developments, scientists have observed that El Niño conditions are triggering a significant transformation in the current hurricane season, raising concerns among meteorologists, our emergency planners, and coastal communities who rely on seasonal forecasts to prepare for potential storms. This shift is not just a minor variation in weather patterns, but a large-scale atmospheric change that affects ocean temperatures, wind behavior, and storm formation zones, ultimately altering how hurricanes develop, strengthen, and travel across the ocean. El Niño occurs when surface waters in the central and eastern Pacific Ocean become warmer than average, disrupting normal wind circulation patterns known as trade winds, which typically move from east to west across the ocean. And when these winds weaken or reverse due to warming waters, the entire atmospheric balance shifts, causing ripple effects that extend far beyond the Pacific region. One of the most important consequences of this shift is its impact on the Atlantic hurricane season, where storms often form, intensify, and move toward coastal regions such as the Caribbean, the Gulf of Mexico, and the eastern United States. And during strong El Niño events, wind shear in the Atlantic tends to increase, making it more difficult for hurricanes to form and strengthen. Yet at the same time, certain regions may experience more intense storms due to unpredictable atmospheric instability. Meteorologists have been closely monitoring current ocean temperature anomalies, and recent data indicates that El Niño conditions have become more pronounced, leading to noticeable changes in hurricane formation patterns compared to previous years, with some regions experiencing fewer early season storms while others face sudden bursts of rapid intensification, creating an uneven and unpredictable hurricane landscape that challenges traditional forecasting models. This unpredictability is particularly concerning because hurricane preparedness relies heavily on seasonal consistency, and when patterns shift unexpectedly, it becomes more difficult for governments and communities to allocate resources, issue timely warnings, and prepare evacuation plans effectively. One of the most significant impacts of El Niño on hurricane activity is the alteration of vertical wind shear in the atmosphere, which refers to changes in wind speed and direction at different altitudes. And when wind shear is strong, it disrupts the structure of developing hurricanes by tearing apart the storm system before it can fully organize, which typically leads to a reduction in the number of major hurricanes in the Atlantic basin during strong El Niño years. However, this does not mean that overall risk is reduced, because while the total number of storms may decrease, the ones that do form can behave unpredictably, sometimes intensifying rapidly under favorable local conditions, creating sudden and dangerous weather events that leave little time for preparation. In addition to wind shear, El Niño also affects sea surface temperatures in different regions of the ocean, and while warmer Pacific waters are a defining feature of this phenomenon, the Atlantic Ocean can experience complex secondary effects, including localized warming or cooling depending on atmospheric circulation patterns. And these temperature shifts play a critical role in hurricane development, since warm ocean water serves as the primary energy source for tropical cyclones, fueling their growth and intensity. When these conditions align in unusual ways due to El Niño interference, storms can either weaken unexpectedly or strengthen rapidly, making forecasting significantly more difficult. Another important factor influenced by El Niño is atmospheric moisture distribution, which determines how much energy is available for storm development, and changes in global circulation patterns can redirect moisture-rich air masses away from traditional hurricane formation zones or concentrate them in unexpected areas, leading to shifts in where storms are most likely to develop. This means that regions that are typically less affected by hurricanes may suddenly face increased activity. While historically active areas may experience temporary reductions, creating a sense of imbalance in seasonal expectations. Scientists also emphasize that El Niño does not act alone, but interacts with other climate systems, such as the Atlantic multidecadal oscillation and global warming trends, which further complicates hurricane prediction models, because when multiple climate drivers influence the same system simultaneously, the resulting weather patterns become highly nonlinear and difficult to predict using traditional statistical methods. This combination of factors has led researchers to adopt more advanced simulation models that incorporate real-time satellite data, ocean buoys, and atmospheric monitoring systems to better understand how hurricanes may behave under changing conditions. Recent observations suggest that the current El Niño event is not only affecting storm frequency, but also influencing storm structure and behavior, with some hurricanes showing unusual patterns of rapid intensification followed by sudden weakening, a phenomenon that can make storms more dangerous because it reduces the reliability of long-term forecasts and increases the risk of underestimating storm strength before landfall. This has raised concerns among emergency management agencies, which rely on consistent forecasting models to issue evacuation orders and prepare disaster response strategies. As coastal communities are particularly vulnerable to these changes, as even small variations in hurricane intensity or path can have significant consequences for flooding, infrastructure damage, and human safety. And with El Niño introducing additional uncertainty into seasonal predictions, authorities are being urged to adopt more flexible preparedness strategies that account for sudden changes in storm behavior, rather than relying solely on historical patterns. This includes improving early warning systems, strengthening communication networks, and enhancing public awareness about the potential risks associated with rapidly changing weather conditions. While El Niño is a natural and recurring climate phenomenon, its interaction with modern climate change adds a new layer of complexity. As rising global temperatures are already contributing to warmer ocean surfaces and increased atmospheric instability, potentially amplifying certain aspects of hurricane behavior even during periods when El Niño would traditionally suppress storm activity. And this overlapping influence of natural and human-driven climate factors has made it increasingly difficult for scientists to separate individual contributions to observed weather changes. Despite these challenges, researchers continue to monitor oceanic and atmospheric data closely, using advanced satellite systems and predictive models to track El Niño's evolution and its impact on hurricane formation. And while some patterns are becoming clearer, many uncertainties remain, particularly regarding how long the current El Niño phase will persist and how it will interact with other climate variables over the coming months, leaving meteorologists cautious in their long-term forecasts. As the hurricane season progresses under the influence of this strong El Niño event, one thing has become increasingly clear. Traditional expectations about storm frequency and intensity may no longer apply in the same way they once did. And communities that rely on predictable seasonal behavior must now adapt to a more dynamic and unpredictable climate system, where sudden changes can occur with little warning, reshaping the way hurricanes develop and impact the world. As the El Niño pattern continues to strengthen across the Pacific Ocean, its influence on global hurricane activity is becoming even more complex and unpredictable, revealing that the relationship between ocean temperatures, atmospheric circulation, and storm development is far more interconnected than previously understood. And while Part 1 explained how El Niño affects wind shear, sea surface temperatures, and storm formation zones, the second part focuses on the real-world consequences of these changes, including unusual hurricane behavior, shifting storm tracks, unexpected intensification patterns, and the growing challenges faced by meteorologists attempting to forecast a season that is no longer following traditional rules. One of the most concerning developments observed during strong El Niño conditions is the increasing occurrence of rapid intensification events, where tropical storms strengthen into major hurricanes within an extremely short period of time, sometimes in less than 24 to 48 hours, leaving very little time for coastal communities and emergency services to respond effectively. And although rapid intensification is not new, its frequency appears to be increasing under current climate conditions influenced by El Niño, which alters atmospheric stability and allows storms to tap into concentrated pockets of warm ocean water more efficiently than in normal seasons. This behavior makes forecasting extremely difficult because a storm that initially appears weak or disorganized can suddenly escalate into a powerful hurricane just before landfall. Another major effect being observed is the shifting of hurricane tracks, where storms do not follow their usual predictable paths, but instead move in more erratic directions due to changes in steering winds in the upper atmosphere. And El Niño plays a key role in altering these wind patterns by modifying jet stream behavior and atmospheric pressure systems, which can redirect hurricanes toward regions that are not typically accustomed to frequent storm impacts, creating a false sense of security in areas that may suddenly find themselves in the path of a powerful system. This unpredictability adds another layer of complexity to disaster preparedness planning, because historical data becomes less reliable when storm tracks begin to deviate from long-term averages. In addition to changes in storm intensity and movement, scientists have also observed alterations in the structure of hurricanes during El Niño seasons, where some storms exhibit unusually asymmetric formations, uneven wind distribution, or irregular eye development, suggesting that atmospheric conditions are interfering with the normal organization process of tropical cyclones. And while some of these storms weaken due to unfavorable wind shear, others manage to reorganize rapidly under localized favorable conditions, resulting in unpredictable cycles of strengthening and weakening that challenge even the most advanced forecasting models currently in use. These structural irregularities also affect rainfall distribution associated with hurricanes, leading to extreme precipitation in localized regions while leaving other nearby areas relatively unaffected. which increases the risk of flash flooding, landslides, and urban water management failures, particularly in densely populated coastal cities where drainage systems are not designed to handle sudden concentrated downpours of this magnitude, and as a result, even weaker storms can produce severe flooding impacts when atmospheric moisture conditions are amplified by El Niño-driven circulation changes. Meteorologists studying current hurricane seasons under El Niño influence have also noted changes in storm lifespan, with some systems dissipating more quickly than expected due to increased wind shear, while others managed to persist longer by repeatedly reorganizing their structure over warm ocean regions, creating extended periods of uncertainty for forecasting agencies. And this inconsistency makes it difficult to determine the true threat level of any given storm until very late in its development cycle, which reduces the effectiveness of long-range predictive warnings that communities traditionally rely on. Another critical aspect of El Niño's impact on hurricane activity involves its interaction with global climate change, as rising sea surface temperatures across the world's oceans are already contributing to more energetic storm systems. And when combined with El Niño conditions, the effects can either amplify or suppress hurricane activity depending on regional atmospheric dynamics, creating a highly unstable and nonlinear climate system where small variations in temperature or pressure can lead to significantly different storm outcomes. And this complexity is forcing scientists to develop more advanced computational models that integrate real-time satellite data, ocean heat content measurements, and atmospheric simulations to improve prediction accuracy. Emergency management agencies are also adjusting their strategies in response to these evolving patterns, shifting from purely seasonal prediction-based planning to more dynamic response systems that can adapt to rapidly changing storm behavior, including pre-positioning resources in multiple potential impact zones rather than focusing on a single predicted path, and enhancing communication systems to ensure faster dissemination of warnings to the public. Because the increasing unpredictability of hurricane behavior under El Niño conditions means that traditional preparedness models are no longer sufficient to guarantee safety. Coastal infrastructure is another area of growing concern, as bridges, roads, power systems, and drainage networks in many regions were designed based on historical storm data that may no longer accurately reflect current or future hurricane behavior. And with storms becoming more intense or shifting paths unpredictably, there is an increasing risk that existing infrastructure may be overwhelmed by events that exceed their original design parameters, prompting discussions about the need for updated engineering standards that account for more extreme climate variability influenced by both El Niño and long-term global warming trends. In addition to physical impacts, El Niño-driven hurricane changes are also affecting economic systems, particularly industries such as agriculture, insurance, tourism, and energy production, where unexpected storm behavior can disrupt supply chains, damage crops, increase insurance claims, and halt coastal operations, leading to significant financial consequences that extend far beyond the immediate impact zone of any single hurricane. And as uncertainty in forecasting increases, economic planning becomes more difficult for both governments and private sectors. Scientists continue to emphasize that while El Niño is a natural climate cycle that has existed for thousands of years, its current behavior may be interacting with modern climate conditions in ways that are not yet fully understood. And this combination is creating a new level of complexity in hurricane science that requires continuous observation, improved modeling, and international collaboration to better understand how these systems will evolve in the future, especially as global temperatures continue to rise and ocean heat content increases across all major basins. Despite these challenges, ongoing research and technological advancements in satellite monitoring, atmospheric modeling, and oceanographic data collection are gradually improving our understanding of how El Niño influences hurricane seasons. And while complete predictability may never be possible due to the inherently chaotic nature of weather systems, scientists are becoming better equipped to identify early warning signs of rapid changes in storm behavior, allowing for earlier alerts and improved disaster preparedness strategies. As this El Niño-driven hurricane season continues to unfold, it is becoming increasingly clear that the relationship between oceanic and atmospheric systems is more delicate and interconnected than previously believed. And even small shifts in temperature or wind patterns can cascade into large-scale weather events with serious consequences for millions of people living in vulnerable coastal regions, making it essential for both scientists and communities to adapt to a future where traditional weather patterns may no longer provide reliable guidance for predicting hurricane behavior. And, as monitoring continues, one key question remains unanswered: whether future El Niño events will continue to intensify hurricane unpredictability, or whether improved understanding of these systems will eventually allow humanity to better anticipate and prepare for the dramatic changes they bring to global weather patterns. A question that remains at the center of ongoing climate research and meteorological debate.